Good morning, good afternoon, or good evening, Sip&Talkers, depending on where you are in the world. And welcome back to Sip&Talk.
Hey, everyone, and welcome to what we are officially labeling EP500. We made it.
I know, right? 500. We really pulled out all the stops for this one. This has been brewing for a whole week, just compiling some incredible research. I don't know about you, but my coffee today, it just smells particularly ambitious.
It really does. Maybe it's just the sheer intensity of the topic. We've been diving into the newest oncology data, all the whispers that AI, precision medicine, and even cancer vaccines might hit these huge milestones before 2030.
Yeah.
And, I was about to really get into the weeds on the technical papers, and you just casually lean over and say, optimism is the greatest anti-cancer weapon.
Huh.
And I just thought, wait a minute, since when did you become a motivational guru?
I've always been motivational. You weren't paying attention. But seriously, with a topic like this, the future of oncology, if you don't have some level of optimism, it's almost impossible to face.
That's true.
Breakthroughs in this field, they feel like 10 years condensed into one day, and then the next day stretches on for 10 years. It's a real marathon of patience.
It really is. And when people talk about cancer, the default reaction is just fear, a sense of heaviness. We've touched on related things before.
Oh, yeah?
We had that deep dive on music potentially destroying cancer cells. That was EP102.
Right.
Then the one about whether only humans get cancer, EP156, and our look at global lung cancer, which was EP372. If you're interested, you can always go back and listen.
But today, this feels different.
It feels fundamentally different. The more I looked at the current data, the more I realized that this might be the moment humanity can finally stop thinking about, total eradication.
Yeah, that sort of silver bullet idea.
Exactly, and start focusing on something much more achievable, compression and domestication. Turning cancer into a controllable chronic disease.
I love that framing, compression and domestication. It sounds like we're finally learning how to live with and manage this incredibly dynamic biological foe.
But it requires rational optimism. Not the blind kind, but the grounded belief that progress is accelerating and that we can be a part of it.
Exactly. Optimism isn't naivety. It's the capacity to understand the risk, but still choose to move forward anyway. I mean, science runs on optimism.
Right.
A pessimistic researcher isn't going to stick around for a trial that only shows results after a decade. Medical revolutions are basically completed by the relentless optimists.
I completely agree. So for this special deep dive, we're going to analyze the strategic prospects for oncology in 2030. We're asking 3 sort of core questions for the next decade.
Okay, let's lay them out.
First, how exactly does AI function as the accelerator in all of this?
Number 2.
Is precision medicine truly mature? And is success, and by success we mean control, is that actually possible by 2030?
And the third big one.
Will cancer vaccines be the next great wave of therapy? And I think most importantly, do all these breakthroughs combined give us a real foundation for, reasonable optimism about where we'll be in 2030?
All right, let's find out. Let's start with the revolutionary engine driving all this change. Artificial intelligence. I mean, it's the non-biological driver making everything else faster, cheaper, and a lot smarter.
Let's sip and let's talk.
Okay, so let's unpack this. AI is the catalyst, the core technology that underpins everything else we are going to talk about today. It's really fundamentally shifting the entire cost-benefit ratio of cancer care.
It is the engine of the revolution. And the first place we see its power is in redefining early diagnosis and screening. It's giving us this massive boost in efficiency and accuracy right where we need it the most.
You think about the strain on radiology departments globally. There are just too few experts and this overwhelming volume of really complex scans. And that leads to burnout. And frankly, it sometimes leads to missed details.
Of course.
Especially when, a human's attention starts to fade after looking at hundreds of images a day.
Precisely. And the data points here are just stunning because AI addresses both of those human limitations at the same time. I mean, look at mammogram screening, which is the cornerstone of early breast cancer detection.
Right.
Our sources are showing that AI-supported reading can detect 20% more cancers than the traditional method of double manual reading.
20%. That's a huge number of lives we're talking about, just by improving sensitivity.
It's massive. It means fewer false negatives and much earlier intervention. It turns a tool that's already effective into, like you said, a truly formidable weapon.
But, okay, the other side of that coin is the workflow. Because if the AI is just adding more complexity for the doctor, it ultimately fails.
But it's not. That's the beauty of it. It's streamlining. By taking on the laborious, repetitive comparison tasks, and let's be honest, the vast majority of images are normal,
Right.
AI simultaneously reduces the radiologist's workload by an astounding 44%. Imagine being able to nearly halve your tedious reading time while increasing your detection rate by a fifth. This dual benefit, speed and accuracy, is why the uptake is happening so fast. It frees up the human expert to focus their energy on the really ambiguous high-risk cases.
That reduction in cognitive fatigue must be immense. And this isn't just theory anymore, is it? We're seeing real-world regulatory milestones.
Exactly. The FDA's approval of expanded digital pathology systems for use in primary diagnosis, that's happening as of June 2025. This isn't some pilot program. These tools are being approved for routine, frontline clinical decision-making.
That's a huge step. It signals trust and validation.
It is. But the real game changer, I think, is how AI handles information. It's this concept of multimodal data fusion. It finally overcomes the data silos that have held back personalized oncology for decades.
I can see that. The traditional system forces doctors to be the fusion engine themselves, right? They're manually trying to connect genomic results on one screen with physical pathology slide and a PET scan from a totally different hospital system.
It's detective work, not medicine.
Yeah. AI just demolishes those barriers. It integrates all these diverse data streams, genomics, imaging, pathology, clinical records, and creates a unified predictive system. It sees the patient not as a pile of separate reports, but as a single complex system.
They can find connections we'd never see.
Exactly. It can simultaneously compare, say, the protein expression it sees in a pathology image with the specific mutations found in the genomic data to predict how aggressive a tumor is likely to be.
A great example of this is that sequential screening model for something like colorectal cancer. You said this moves us toward a functional conquest. I like that term.
It's about preventing the late-stage disease before it even fully develops. The old model was, high-volume, expensive, invasive screening for everyone over a certain age, the colonoscopy.
Right. Everyone's favorite procedure.
The new model, with AI, is highly targeted. It pushes the diagnosis way upstream.
So walk me through that sequence. How does it start? It starts with the most non-invasive and cheapest step, molecular detection. So think specialized stool sample kits or advanced blood tests, these gene methylation kits.
Okay.
AI processes the results from these kits to screen a massive, healthy population, and it just flags the individuals who show high molecular risk markers. The kits are cheap, they're easy to distribute, and it dramatically reduces the need for initial invasive screening.
So we're not even waiting for symptoms or visual polyps anymore.
Yeah.
We're detecting a molecular signature of future risk. It's like a warning light on the dashboard.
Precisely. And you only target those high-risk patients. Then you move to the second, more resource-intensive step, an AI-assisted smart colonoscopy.
And the AI is helping in real time.
Yes. The AI uses its preloaded knowledge, informed by those molecular markers, to assist the specialist. It can highlight subtle, flat lesions or high-risk changes that a human eye might miss during a long procedure. It makes sure that the invasive steps are applied with incredible precision.
That dual-layer approach, molecular screening first, then AI-assisted diagnosis, that seems like a blueprint for managing all major solid tumors by 2030. It's smart resource allocation, powered by data.
It's the move from firefighting to preventative maintenance.
So let's move to the next step. Using AI to drive precision medicine by reading the tumor's molecular logic. This feels like the big intellectual shift, from just size and spread to understanding the molecular individualism of the cancer.
It's a huge philosophical leap. For decades, right? Stage 3 lung cancer in patient A was treated pretty much like stage 3 lung cancer in patient B. Now, AI lets us decode the specific hallmarks of cancer for that individual tumor.
What exactly are these hallmarks? I've heard the term, but it sounds a little generalized. Can you break that down?
Yeah, so think of the hallmarks as the 10 specific biological capabilities a cell has to acquire to become a malignant cancer. It's like the rule book the tumor is following. They include classic things like resisting cell death, achieving unlimited replication, promoting genomic instability to create more mutations, and crucially, growing its own blood vessels and evading the immune system. A tumor doesn't just grow, it actively programs itself to defeat all the body's regulatory systems.
So AI isn't just reading the genetic mutations, it's identifying the specific strategy the tumor is running based on which of those hallmarks are active. Is that right?
That's exactly it. And this explains the huge variation in outcomes we see. Two patients might have anatomically identical stage 2 breast cancer, but if one tumor has a dominant program for immune evasion and the other has one for rapid growth, their prognosis and treatments are totally different. AI analyzes these incredibly complex interactions.
And the research proving this is just massive in scale. You mentioned a study that involved millions of cells.
It's hard to even grasp. Researchers used a new AI system to analyze an unprecedented 3.1 million individual cells from 14 different cancer types. They created these synthetic pseudobiopsy samples.
Pseudobiopsies. Why not just use the real thing?
Because a physical biopsy is just a snapshot in time. By creating these digital models, they could simulate the tumor's progression. They could watch how the different hallmarks interact and how their collective activity gets stronger as the disease goes from early stage to metastatic.
So you can see the whole life cycle.
You're essentially reverse engineering the tumor's strategy and finding its weak points at every stage. That kind of dynamic analysis is only possible with AI simulation.
And once AI reads that logic, that translates directly into personalized treatment guidance.
Right. It lets doctors select drugs that specifically target the patient's active molecular markers instead of relying on generalized protocols. If the AI says this tumor is completely dependent on this one metabolic pathway, the doctor can immediately choose a drug that shuts down that pathway.
Which would be a huge advantage in cancers that are known for being unresponsive, like pancreatic cancer. That's always the poster child for difficult malignancies.
Absolutely. For years, clinicians have used standard chemo, but the response rates were, highly variable and often pretty disappointing. Now, AI data models are showing success in predicting which initial chemo regimen will be most effective for that specific patient based on subtle clues a human review might miss.
And why is optimizing that initial regimen so critical in something like pancreatic cancer?
Because the disease moves so fast. Survival depends heavily on minimizing the time you spend on ineffective treatment. Every wasted week on a toxic regimen that isn't working is precious time lost, letting the cancer gain momentum.
So AI optimizes the very first move.
Exactly. It maximizes the probability of a successful outcome from day one, minimizing delays and avoiding unnecessary, debilitating side effects.
The final piece of this AI puzzle is how it accelerates drug discovery and manufacturing. Before AI, this process felt almost artisanal. A lot of luck and brute force chemistry.
It was so slow and resource intensive. Now you have AI algorithms, robotics, and digital biology all working together. They can identify new clinical drug candidates in just several months instead of the several years it used to take.
That's an exponential gain.
It is. It's going to fill the clinical pipeline with options we don't even know exist yet.
And that speed is absolutely vital for the future of vaccines, especially the mRNA platforms we're about to discuss. Because even if you have the perfect target, you still have to deliver it.
100%. The success of mRNA vaccines relies entirely on their delivery system, the lipid nanoparticles, or LNPs.
The LNPs, those are the microscopic shields, right? The delivery truck.
They are. They protect the fragile mRNA from getting destroyed and ferry it into the cells. But designing the perfect LNP is incredibly complex chemistry. You need the right size, charge, stability, everything.
And this is where AI steps in to predict the optimal recipe.
Correct. Instead of agonizing trial and error in the lab, AI trains machine learning models on thousands of existing delivery particles. It analyzes their structure and their efficacy, and then it predicts the optimal composition for new LNPs tailored to specific vaccines.
So it speeds up development by how much?
By months, sometimes years. It's a huge accelerator. And the market confidence in this whole transformation is just immense.
Right, the numbers. The global AI and oncology market is predicted to hit, $11.2 billion by 2030.
With a compound annual growth rate of 29.4%.
Wow.
That CAGR is a screaming signal. This isn't speculative anymore. This is deep strategic capital flowing into a technology that is universally recognized as the core tool for the next generation of cancer breakthroughs. AI is the infrastructure.
Speaking of that infrastructure, that brings us perfectly to the output of this acceleration. Cancer vaccines. Let's dive into part 2 and the race for scalable, shelf-ready immunity.
So the core challenge here is simple, right? We need to move beyond this ultra-expensive, bespoke customization toward solutions that are scalable, affordable, and shelf-ready.
It's the difference between personalization like a custom suit and universalization, a great mass-produced jacket that fits most people perfectly.
That's a great analogy. And the high-tech, high-cost side is the personalized neoantigen vaccine, or PCV. These things are brilliant, bespoke solutions.
But what are they targeting exactly?
They target neoantigens. These are the unique mutated proteins that are found only on the surface of a patient-specific tumor. The immune system, which is normally blind to the tumor, learns to recognize these unique signatures.
And then the T cells can go in and specifically target only the cancer cells.
Exactly. The process is straight out of a futuristic lab. It relies entirely on AI to integrate vast amounts of data DNA, RNA, proteins, along with the patient's specific HLA typing.
The HLA typing is what determines how the immune system presents these targets, right?
Right. So the AI predicts exactly which mutated antigen will bind most effectively and trigger a really strong tumor-specific T cell response. It is truly one drug, one patient.
But if the technology is that good, what's the barrier? Why isn't this the immediate universal solution?
The limitations are financial and logistical. I mean, the cost is just astronomical. It often exceeds $150,000 per patient.
150. Wow. That immediately restricts access to a tiny fraction of the global population.
It's a miracle technology, but it's only accessible in these high-resource, centralized environments. And then there's the time factor, which is just as restrictive, especially for aggressive cancers where every single week matters.
Right. If you have to wait 3 months for your personalized vaccine, the patient might be beyond help by then.
The entire process, the biopsy, the sequencing, the AI prediction, custom manufacturing, quality control, it's incredibly complex and slow. It takes 8 to 12 weeks.
So PCVs are technically superior in their specificity,
Yeah.
but they're economically and logistically limited for most of the world.
Which is why the solution for global equity has to be the universal mRNA vaccines, or UCVs.
Okay, so these are the path to global equity because they are non-tumor specific.
Right. They leverage general inflammatory markers, specifically things called PAMPs and DAMPs, to trigger a robust innate immune response instead of needing a personalized sequence. They're like a general alarm bell for the immune system.
And that general off-the-shelf approach is what makes them so much cheaper and simpler to produce.
Predictably up to 100 times cheaper than PCVs. They're genuine off-the-shelf products. You eliminate the need for personalized sequencing, weeks of complex manufacturing, all of that. And this simplicity is revolutionary for global access.
The big scientific question is, if it's not specific to the tumor, how does a universal vaccine generate a powerful, specific anti-tumor response? How does it even compare to PCVs?
That is the brilliance of a mechanism known as epitope diffusion. This is the key. UCVs work by transforming these typically non-reactive silent tumors, what we call cold tumors, which make up about 70% of solid cancers, into inflammatory reactive microenvironments.
So the goal is to just turn up the heat on the tumor, make
Yeah.
it visible to the immune system. It's like shining a massive spotlight on a criminal who thought they were hiding in the dark.
That's exactly it. The UCV doesn't fight the battle itself, it ignites the war. The vaccine provides that initial, non-specific inflammatory signal, and the resulting chaos allows the immune system to discover its own previously hidden tumor targets.
Okay, let's break down the molecular phases of this epitope diffusion, because this mechanism sounds elegant and really critical to this whole 2030 vision. So phase 1, initial activation.
Phase 1 happens fast within the first few hours after injection. The LNP delivery system, perfected by AI, activates these crucial innate immune receptors inside our cells, specifically TLR78 and RIGI. These receptors are basically a cellular surveillance system normally programmed to detect viral RNA.
So the UCV RNA entering the cell expertly mimics a sphere of viral infection.
It tricks the cell into thinking it's under siege by a major pathogen, and this triggers this massive signaling cascade that results in the rapid secretion of a powerful immune signal called type I interferon. This interferon is the universal immune alarm.
And that alarm, that inflammation, then drives phase 2. APC maturation. What's happening in the tumor environment now, say 6 to 24 hours later.
That inflammatory state rapidly matures our antigen-presenting cells, specifically dendritic cells, or DCs. DCs are the generals of the immune system. They grab antigens and present them to T cells. But critically, this inflammation also increases the tumor cell's own MHCI expression.
Okay, why is increasing MHCI expression so important for the immune system to finally see the tumor?
So MHCI molecules are like little display stands on the surface of almost every cell. Healthy cells use them to show the immune system, hey, everything's normal in here. But tumor cells often shut down MHCI to avoid being seen. It's their invisibility cloak. When the UCV-driven interferon forces the tumor to display more MHCI, it enables the processing of previously hidden or cryptic tumor epitopes. The tumor loses its camouflage.
So the DC cells are now mature and active. The tumor cells are vulnerable and displaying all these hidden targets. And that sets up phase 3. Cross-presentation.
Right. This happens over the next 24 to 72 hours. The highly activated DCs take those newly discovered cryptic tumor epitopes antigens generated by the tumor itself, not the vaccine, and they process them. Then they present these specific customized targets directly to T cells. And this crucial process overcomes something called peripheral tolerance.
Peripheral tolerance. That's essentially the immune system's self-imposed speed limit, right? To prevent autoimmune disease.
Exactly. And tumors hijack this tolerance, convincing the T cells that they're self and should be ignored. The massive targeted inflammatory signal from the UCV breaks that specific tolerance within the tumor microenvironment. It recruits previously inactive T cells and turns them into specific tumor killers based on what the DC discovered.
And the last stage is what matters for long-term survival. Phase 4, memory and diversity. We need this response to be durable.
By the time we hit the 3 to 14-day mark, this broad activation results in durable immune memory. The key term here is molecular and intermolecular diffusion. It means the immune system develops memory not just for one or two targets, but for multiple different parts of the tumor.
So it's a broad, durable response that's much less susceptible to the tumor's ability to mutate and escape.
Precisely. It sounds like the UCV is this smart, necessary trigger that ultimately provides a highly customized response, but without the high cost and time of PCV manufacturing. It's scalable genius.
It really is. For global oncology, UCVs seem like the only realistic strategy for universal equitable management by 2030. They have that perfect blend of technological power and scalability.
Exactly.
All right, now we get to the big question. We have the AI, we have precision tools, we have these scalable vaccines. Can we actually conquer cancer by 2030? And I guess the answer, as always, depends entirely on how we define conquer.
We have to start with the cautious scientific view. A universal cure. One shot that eradicates all forms of cancer forever that is highly unlikely by 2030. We're still facing these fundamental biological constraints.
Right, like the massive internal variability of the disease itself.
Exactly. Tumor heterogeneity, the fact that different subclones within the same tumor are rapidly mutating and developing different resistance mechanisms, and the rapid pace of immune evasion, it just means cancer is too diverse, too dynamic for a single silver bullet.
So we abandon the cure definition, and we embrace the optimistic technological definition. Systemic functional management.
That is the realistic 2030 goal. It means turning most aggressive cancers into controllable chronic diseases. Think HIV or type 1 diabetes. Not cured, but managed indefinitely with effective regimens that allow for a high quality of life.
And the key to managing them is monitoring minimal residual disease, or MRD. That's our new definition of success, right?
MRD monitoring is absolutely essential. Using these highly sensitive tools like circulating tumor DNA or ctDNA, these liquid biopsies, we can detect tiny traces of cancer in the blood long before it can form a symptomatic mass.
Which allows for timely intervention.
Right. So the strategy is clear. AI enhances early detection, precision medicine like ctDNA improves how we stratify patients, and UCVs reduce the risk of recurrence. Functional management is the definition of a 2030 victory.
That said, this technological potential is just that potential if we can't implement it globally. So we have to face the major barriers to widespread success.
And the first one is a little counterintuitive, the clinical implementation burden. The problem isn't the availability of the tech, it's the overload of tech on the front lines.
I can totally imagine that. Doctors are already managing complex electronic health records, and now we're handing them 5 different AI algorithms for 5 different tasks.
Exactly. They have too many AI tools, too many specialized tests, and not enough time or standardized training to figure out which ones are effective and trustworthy. The AI has to integrate seamlessly into the workflow to reduce the burden, not add another 5-minute step to charting.
And AI is famously garbage in, garbage out. Its success depends entirely on data quality and trust, which brings us to the next set of barriers.
The data landscape is a mess. We have these massive data silos and inconsistencies. AI needs standardized, huge data sets to train accurately, but medical data is scattered across different hospitals, proprietary systems, and it's all formatted differently.
So one hospital's report can't talk to another.
We urgently need global adoption of unified standards, like SNMCT for pathology, to make data interoperable. Without that, AI can only ever be locally smart, not globally brilliant.
And then there's the trust issue, the black box problem. Clinicians are the ultimate decision makers, and they need to understand why the AI is telling them to do something.
This is a major hurdle. Many of these cutting-edge AI models lack what's called explainability, or XAI. They give a diagnosis or a recommendation, but they can't tell the human doctor why it made that choice. And doctors are, understandably, reluctant to trust life-and-death advice if they can't understand the reasoning.
It creates a legal and moral impasse. If a drug fails, the doctor needs to know why. Did the AI miss something? Without that explainability, the doctor bears all the liability.
And on top of that, there's the risk of algorithm bias. If your training data primarily features patients from one high-income ethnic group, the AI will perform flawlessly for that group, but disastrously for an underrepresented population.
So it could actually make health inequality worse.
It could embed our historical biases into the future of medicine. And finally, the biggest bottleneck: global equity and cost.
Yeah.
Oncology and care costs in high-income countries are projected to exceed $500 billion annually by 2030.
$500 billion.
This financial barrier is the single biggest impediment to universality. It means resource-poor countries just cannot afford these individualized treatments or the AI infrastructure required.
This leads us directly to the layer of strategic competition, geopolitics, and the research landscape, specifically between the U.S. and China. This tension is a fascinating double-edged sword. It hurts collaboration, but it accelerates domestic investment.
It's the ultimate zero-sum gain scenario. But we have to look objectively at China's unique contribution here. Their advantages are primarily about scale and speed.
The data advantage is immense, right? Especially for AI training.
China has the largest single-race medical data set in the world. For AI models that need massive scale to train accurately, especially for cancers prevalent in Asia like liver or gastric cancer, that's a critical foundation. It improves the global understanding of these regional variations.
And their centralized system allows for incredibly rapid clinical trial acceleration.
Yes. The sheer size of the patient pool and the streamlined regulatory environment mean they can recruit for trials extremely fast. This speeds up validation of new drugs and advanced therapies. There have been times where China's CAR-RT trial registration numbers have actually outpaced the U.S. That rapid validation cycle is a major asset for the whole world.
But rapid validation doesn't automatically mean global adoption or foundational breakthroughs. And there are challenges when it comes to integrating this into the global system.
For sure. The first is a focus on originality versus application. A lot of the research, particularly in drug development, tends to be me too or me better optimizing existing drugs rather than truly foundational first-in-class breakthroughs.
And the other persistent issue is data governance and transparency.
Right. Regulatory differences, concerns over data security and cross-border transfer, they make Western approval from the FDA and EMA really difficult. If the data standards aren't globally trusted, the innovations, no matter how fast they're validated, will be limited to specific regions.
So you could end up with two separate, non-interoperable oncology ecosystems by 2030.
It's a real risk. The scientific race is now completely tangled up with international politics, and that's an unavoidable complexity of the 2030 outlook.
All right, before we wrap up, let's take that philosophical detour we promise. A lot of people, when they think about cancer, they think of it in these simple human terms. Is cancer just confused cells that forgot their jobs? The lost cell metaphor.
It's a very common, almost comforting metaphor. The idea that cancer cells are misguided or lost rather than just malicious invaders. This often stems from holistic views or even some fringe scientific theories, like the idea that under stress, cells revert to an ancient single-celled survival mechanism.
It suggests the cell can be corrected, that it can find its way back.
Exactly. But the scientific reality, as we've been discussing with the hallmarks, is far more aggressive and permanent than just forgetting. I mean, it's not simple forgetfulness. Cancer is a systemic, multi-step genetic failure. It involves sequential DNA mutations, the failure of tumor suppressor genes. The cell hasn't just misplaced its instructions, it has permanently lost them. It's a new entity.
So if the cell is genetically broken, how can we possibly guide it back home? Does that philosophical metaphor have any scientific parallel in modern therapies?
It does, actually, in a very specific niche, differentiation therapy. This is the scientific version of finding the way home. The idea is to use targeted agents to force the cancer cell to resume its normal function, to mature and then die naturally instead of multiplying forever.
And you mentioned a classic success case that proves this isn't just theory.
Acute promyelocytic leukemia, or APL. It was once a rapidly fatal blood cancer, but today it is highly curable, with success rates off to over 90%.
That's a huge victory. How do they manage to reteach those cells?
APL is treated primarily with ATRA, which is a form of vitamin A, and arsenic agents. These compounds literally reteach the leukemic cells how to respond to normal differentiation signals. The leukemic cells stop acting like immortal stem cells and instead mature into normal white blood cells that then die a normal programmed death.
That's a stunning success story.
It is. It proves that re-guiding cancer is possible in certain situations. And now, AI is attempting to expand that niche dramatically. AI is currently modeling what are called cell fate maps, helping researchers identify the precise point where a cell deviated from its trajectory, the exact wrong turn.
So it's looking at the whole developmental roadmap of a healthy cell and flagging the moment of failure.
Yes. And by understanding that exact point of deviation, AI can suggest drug combinations that might force the cell back on track. It shows that this philosophical metaphor is actually inspiring new scientific approaches.
That's a beautiful intersection of technology and profound human curiosity. It gives a nice, grounded perspective to our overall optimism.
Okay, final summary time for the 2030 outlook on oncology.
The verdict is highly optimistic for managing cancer, not for achieving universal eradication. We are looking at chronic control for most aggressive diseases through this idea of systemic functional management.
The strategic pathway forward is clear. It's the integration of AI for speed and precision. It's highly targeted medicine. And crucially, it's the massive global scalability of universal mRNA vaccines, the UCVs.
And what remains the single biggest challenge that will determine the ultimate reach of this whole revolution?
It's global equity, universality. The technology exists, or will soon exist, to manage cancer effectively. The failure point will be the financial and logistical barriers that prevent those benefits from being shared beyond high-income zones.
Which leads us to our final provocative thought for you to mull over. Given the immense competitive investment in AI and biotech in both the U.S. and China, the ultimate test won't be which country develops the best vaccine or the smartest algorithm.
No.
It'll be which nation, or perhaps more realistically, which international coalition first successfully manages the complex ethical and logistical nightmare of data sharing and standardization to allow AI to truly learn globally.
The technology is racing ahead. The global governance mechanisms still have a massive amount of catching up to do if we want the benefits to be universal.
All right, Sip and Talkers, that wraps up this special deep dive. We hope this analysis has given you some reasonable optimism and some new avenues for thought.
If you enjoyed this level of depth and synthesis, please subscribe to Sip and Talk wherever you get your audio content. That way, you won't miss any of our future deep dives.
And a huge shout out to our friend Mickey and his YouTube channel, Mickytolife. He always has hilarious content, the newest travel vlogs. Make sure you check him out, have a good laugh, and, boost those natural killer cells.
And thank you. Because of your incredible support, we are back in the top 100 on the charts. We truly appreciate all the support and encouragement.
We'll catch you on the next one.
Goodbye for now.